Okay, so what we are saying now is that your load is decomposed into two components, your alpha. Okay, this is, and the load is inclined at an angle of alpha from the y-axis. Okay, that alpha, and we have got another axis which is the principal axis, and that is located at an angle of beta. Please note that alpha and beta, they are not the same. That's what you get from this equation. Y by z is not equal to tangent alpha. You have got this component also. If you make these two equal, or in other words, if it's a square cross section, in square cross section your IZZ and IYY will be equal, won't it? Then you can say that beta and alpha are equal. But in case of rectangular section, no, they are not equal. Okay, so this is an important thing to appreciate, that your load is the beta and alpha, they both are different. Alpha is the angle, is the inclination of your applied load. Beta is actually the inclination of your principal axis, the neutral axis. Okay, with respect to the centroidal axis. So when I say centroidal axis, this is actually the actual centroid of this cross section. Okay, so the neutral axis can change based on the applied load. The centroidal axis stays the same always. Why? Because gravity stays the same. Gravity doesn't change. So every cross section will have only one centroidal axis. But the neutral axis will change, and that is a function of the applied load. Okay, so that is an important thing to remember. Now in this case, in the case of this was the simple case of rectangular cross section. So I can give you a very simple problem where the load is applied in this direction, and I can ask you that find out stress for it. Okay, the maximum stress. So how are you going to find it? You will write this equation, and then you find out the stress at the maximum stress at the four corners. At the four corners you will have maximum stress, isn't it? Okay, so if I've got my principal axis in this direction, y positive, z positive, that will give me one stress. Okay, both negative, that will give me another stress. Yeah, y negative, z positive, that will give me one stress, and y positive, z negative, that will give me another stress. So you have to find out four stresses. Okay, so in other words, you will have a force in this direction, which is a tension force. This will be a tension force in this direction, and there will be a compression force in this direction. Okay, so this cross section will be in tension and compression. So that's all I can ask you, or I can ask you in this type of equation. I can ask you that find out the inclination of principal axis. So you can give me the principal axis. Okay, so these are the two different ways that I can pose you a question. Now the story, so far whatever we have done, the story was limited to rectangular cross section, which is a symmetrical cross section about both axes. What happened if our cross section is different? Okay, if our cross section is different, like for example, I've got a z axis. Or I've got a angle cross section. Sorry, I've got z cross section, or I've got angle cross section. Now what do you think? Let us see. Okay, make your concept. Problem will be getting solved automatically. If your concept is not developed, you can't solve a problem. Okay, so let us make our concepts. Okay, what is this? Now this is an unsymmetrical cross section in both the axes. It's important. If this was an unsymmetrical cross section in one axis, then we would have had issue of shear center, of shear center. Yeah. Okay, shear center was a phenomena in a cross section which had one axis of symmetry. In this topic, we have got cross sections which have got two axes of which we have got in which we have got no axis of symmetry, or two axes of unsymmetry. So, for example, if I take a cross section like this, and these are the two axes. Now, would my my be 0 in this case? What do you think? Look at that one, y times z. Again, y is this one and z is this one. Okay, so extend it to this one. This is y. If I have got a cross section like this one, look at this. Is yz equal to 0? Integral? The answer is no. Why? Let us test it. Okay, let us test it. I've got an area over here which is, it has got y positive and z is negative. Okay, z is negative and y is positive. Then I need an area which has y. How would I make that 0? I need an area which has got both of them positive. That's how I would make it 0, isn't it? This has got y positive and z negative. I need another area which has got y positive, y and z both positive, isn't it? Agreed? Opposite or whatever, but even if it's opposite, okay, even if it's opposite, that would also be that would also be acceptable. But y and z, the product must be positive. Yes? Do we have any area? No. So this guy is the perfect candidate for unsymmetrical bending. If you put your load in this direction, this will bend about y-axis. Do you get my point? Similarly, this guy, look at this guy. It's the same thing. It's the same thing. I've got this area which has got x negative, y negative. So it is positive. Do I have another area which has got negative? So I won't have. So you can see that these two, the axes which I have defined over here, they are not the principal axes. The principal axes would be somewhere like this. Okay, you have to rotate it in such a way that you get an area where you get that thing equal to 0. Okay, and similarly in this case. So in that case, it was the load which was applied at some inclination with the neutral axis, with the centroidal axis. Okay, it was the load. The cross section was symmetrical. In this case, your cross section is unsymmetrical. So clearly, it's a candidate for unsymmetrical bending. So you have to check. You have to work out its principal axis, and you have to apply the load on the principal axis. Okay? So I can give you either this cross section or that cross section, and you will have to find out then the application of the load. Okay? If I have if I have got, for example, a T section, now T section is again, this is a type of a cross section which is similar to that one. If the load is applied along this direction, okay, so no unsymmetrical bending. If the load is applied at some inclination alpha, then you have to use the same formula. That one. Okay? So T section, which is having one axis of symmetry, that is also similar to this one. If you apply the load on the centroidal axis, it's okay, you won't have unsymmetrical bending. But the problem is with these guys, these cross sections, if you apply the load at centroidal axis, you will automatically get unsymmetrical bending. So you have to apply the load on the principal axis, and you have to find that. Can you distinguish this thing and this thing and this thing and this thing? These are two different. Can you see that? Okay, so that is your topic on unsymmetrical bending. The problems which will be in this topic that are in, I can give you, that is in chapter 6, bending of Hibbler book. I have got 328 page, and all the examples you guys have to do. Okay, chapter 6, 6.5, unsymmetrical, only unsymmetrical. 6.5. Topic 6.5 is unsymmetrical bending, and you guys have to do all the examples.
So assignment है.
This is your second assignment. ठीक है ना? So your first assignment is also due.
मैं बंद कर लेता हूँ.